In the next subsection of this unit, we'll put these two things together, the ideas from simple methods of how to parallelize string matching and this new concept of periodicity of strings. And it will lead to something that's called string matching by duels. If that doesn't sound exciting, I don't know what. Let's see where that comes from. Another little consequence of having a period is that you can align the strings on top of each other. And if you don't have a period, there must be a reason why you don't have one. So let's assume that we have a given pattern that does not have a certain period p. Then that means there must be a witness position that shows us why there can't be this period p, right? And well, it's denoted by omega here, little omega. So it's just a position in the pattern where if you shift it over by p positions, you have a mismatch. That position then witnesses against the periodicity, against the period p, right? Is it clear? Like when I have a non-period p, some number that is not a period of the string, there must be some position where there is a mismatch. Otherwise, it would be a period. So in pictures, if I shift this over by p and it's not a period, well, there must be one position here. If these are all matches, there must be one position where the two characters are not the same. Up here and there. Otherwise, it would be a period. And so then this position is our omega. This is omega plus p. Okay? That's a fairly simple concept, but it's quite interesting and useful because it allows you to exclude guesses. And here's how. If you have a pattern that does not have a certain period p, then whenever you have two positions in the text that are p apart, only one of them can be a match. Maybe none of them is a match, but they cannot both be a match, simply because that would mean a contradiction according to the witness. So suppose both were a match, then we would have the position starting at the second occurrence, and omega positions into the pattern. So that would be the same as p of, so that's the position in the text, and that would be the corresponding position in the pattern. But this is not the same as the position p shifted by the witness definition. But this again would have to be the position in the text that's using the same equality here. It's just using the second match. And these two are the same, so, right? The parenthesis doesn't matter. So these are not equal according to that. And that's a contradiction because, I mean, it's the same position in the text. So again, if we have a non-period p out of any two positions that are p apart in the text, I and I plus p, only one can be a match, or maybe none. Another simple observation, but again, useful because now we can do something that's called a duel between those two positions. We can take those two positions and say by checking the position for the witness character against the text, I will either find a match with one or with the other characters. So there's the two characters in the pattern, the one at the witness position and the one p shifted. And the text can at most be one of the two, right? So that's, again, spelled out what's in the inequality above. And so the other can't be a match, so it can be excluded. That's how we can get rid of guesses. All right. Let's see an example. And note here that P is aperiodic. That's not exactly spelled right. That's slightly better. We will discuss this algorithm only for aperiodic strings. And the periodic strings, because they can essentially be reduced to their period, the repeating part, they can be handled somewhat similar, but we won't discuss all the details here. It's just the high-level idea again. But the example for now works fine with this string because it is aperiodic. And let's first compute the so-called witness table, which is for all non-periods, what is a witness against this periodicity. And you can feel this intuitively, like it's not the efficient way to compute it, but it's the manual way to see what's happening. If we shift by 1, then we could potentially have period 1, but well, we don't have period 1 because there's a mismatch at this position. So there's a witness against period 1, namely the index 0 in the pattern. That's this index, and if you shift by 1, you find a mismatch with the character at I plus p. 0 plus p is 1, so that's what we compare with here. Okay? So 2 things. The string does not have period 1, and we have a witness for that non-period. If we shift by 1 more, the string could have had period 2, but actually it doesn't, because at this position you find a witness against this period. Again, the top number is the one that we take in the witness table, and if you add 2, you get to a different character in the pattern. I think the game becomes clear. We find the same for shift by 3. So these are different, so we put the 1 into the witness table. And even 4 doesn't work. We still find a witness against that. And 5 doesn't work either because of this C, right? It doesn't occur anywhere else. And that's it. If you check 6 is actually a period of the string, this is only 1 character matching, but at least not nothing. So the smallest period is 6. And we've proven that by just exhaustively checking all others and writing down the witness against them. And now let's play the duel if we have this text and we try to find the occurrences of the pattern in this text. Now I know there's only one C and you can already kind of guess manually where the occurrence could be, but that's not what we want. We go strictly by these duels. The first 2 is we can play position 0 against position 1. So guess I equals 0 against guess I equals 1. That means we have a potential period of 1, but we know it's a non-period, and we have a witness against it. So we check the position t equals 1 is a B, and that's not the position of, that's not the character of the pattern at omega at 0, which would be an A, right? So we cannot have an occurrence at 1. We might still have an occurrence at 0. We can't tell at this point. But we've excluded from checking the witness position in the pattern against the corresponding one in the text for the two potential matches, for the 2 guesses, that at least this one is excluded. Let's play position 0 against position 2. So remember, after this first round, 0 was still in the game. It could turn out to be a match from what we've learned so far. So we now play 0 against 2. Again, we have a witness against this periodicity, so we won't have a match at 0 and 2. And in this case, 2 says we check position 3. And if you compare the character at omega plus p with come on. There you go. Let's show in the picture what's going on. So this is one potential match. This is the other potential match. Omega 3 means we're taking this character and this character. sorry, we're taking the 3 in this one. 0, 1, 2, 3. So we take this one and okay, sorry, the pattern is longer. That's 2, 4, 7, 7. That's why I didn't overlap. So we take these two. We pick the character in the pattern here, which is the C, and it's not a B, so we can exclude the 0 this time, right? The character that's matched by this guess to that position in the text corresponds to a mismatch, so we can exclude the occurrence at 0. No occurrence at 0, potentially 1 at 2 still. So next one is we compare positions 2 and 3. So again, this one, 7 characters. This is surprisingly hard to do. Okay, our witness is at 0. So we take this one and this one. Now we find the occurrence in this one. In the further shifted pattern is an A, which doesn't match the B. So we can, from that dual, exclude the position 3. Okay, that's how you go through. It's a little tiresome in the example to check, but you always do just a constant number of character comparisons between pattern and text at these positions of omega, omega plus P. And so after each dual, you can exclude at least one of the potential guesses. And so that brings us to the following algorithm, how you make use of this dueling process. And as I said before, for what I describe here, we'll assume the pattern is aperiodic, and we'll cover the periodic case only in passing by saying you can do it somehow similar. We first pick a block size, which is roughly half of the length of the pattern. We know that the pattern is aperiodic, so its smallest period is bigger than m half. And that means we can compute witnesses against all the periods up to this m half. Okay? So aperiodic means these exist. And then we look at blocks of the text of mu consecutive indices. So we block the text up, and this time non-overlapping. And in each of these blocks, we run duals to eliminate all but one guess. So why do we pick the block size like this? Because that's the potentially largest P for which we have a witness against that period. We only assume P is aperiodic. In the previous example, we had a pattern of length 7, and the shortest period was 6, so we could go further up. In general, if we just assume aperiodicity, we can only assume that there's a witness table up to m half. That's why we have to choose the block size like this, a little more conservative. We run these duals, as we've seen in the example. So out of each block, at most one guess can survive. All others are eliminated in one of the duals. And that means out of every block, we only have one guess left. So we can check all of those roughly n divided by m guesses naively and still stay in linear time the length of the text. Okay, that's the idea. This is all sequential for now. We haven't touched on parallelism yet. I want to briefly go through the individual steps to convince you that it's another worst case linear time method. The first step is just computing one number. That's trivial. The second step, computing these witnesses, I'll comment on very briefly later, but it's essentially a twist on K and P. And if you've seen the connection between the shortest period and the failure function, maybe this is not so surprising that the two can be reduced to each other. The third step has n divided by m blocks, roughly. And we do m duels in each. So multiplying that out is linear, order n. And similar in the last step, we have n over m blocks, and at most one guess survives. Well, one guess survives from each block. And we have to check with m comparisons in each block, in each guess. That's another linear time, order n. So overall, we have another efficient string matching method. It has this blemish that, as stated, it only works for these aperiodic strings. That's why in the previous section I didn't include it, because it doesn't really have many advantages over the other methods, except for what's coming now. And the big advantage that it does have is it works in parallel. So this first step, all the steps basically stay the same, but we have to see how we can parallelize things. So the first step, there's nothing really to do. The second step is possible to parallelize, but it's very tricky. I will only tell you what is possible. And a reasonably complicated method gets it down from m to log m squared. But this part will be beyond the scope of the course. But what's nice to show is the other parts. So for each of these blocks, each block can be treated in parallel. They're embarrassingly parallel, right? They don't depend on each other, so that's great. And the duels can be laid out as a binary tree, like this. If you were to play the duels like in the example, always keep the surviving position and compete against the next free position you haven't tried, then the next duel would always depend on the outcome of the previous, and that's bad for parallelization. But if you lay them out like this, then these can all be independent. The bottom row can all play in parallel, and you don't need to know what was the winner of each to play the others. So like a tournament, and then you keep the winners playing against each other until in the final there's only one guess coming out as a potential match. And well, the parallel time is the height of the tree. We've seen this in Unit 3. So that's where this log mu comes from, rounded up to be precise. That's the number of duels, that's the number of duels that have dependency on each other. That's the parallel time. And for the last step, we can do one of the algorithms we've seen before in the first section. For example, the crew RAM that again does a binary tree to do the parallel AND. Yeah, unless this is maybe this is obvious to you, but this way of reordering binary operations into a binary tree, that's exactly what we did for the prefix sum problem in Unit 3. That was the first problem we really looked at for parallelization. And you see that this similar idea is resurfacing in many ways here. Right, so the matching part, what I mean by this is this one. The part that does all the duels and checks the surviving guesses, that's the matching part, and that can be done in log m time, parallel time, and linear work, order n work. So that's pretty much as good as possible. The only slightly more complicated step is this second one. So to compute the witnesses in a sequential algorithm, that is would have been in scope of the class, but since this is about parallel algorithms, I wasn't sure if that adds much to it. A similar algorithm to the computation of the KMP failure function can do this sequentially in theta m time. And the parallel algorithms, unfortunately, are much more complicated. And so I'll just state the results there, but we won't look into those. I want to finish that part and essentially string matching in the way we've seen it by briefly looking at what's known in theory, how quick you can do parallel string matching. If you use this most fancy, sophisticated way of computing the witnesses, you get an order log m time, parallel time, and work efficient string matching algorithm that can run on this crew RAM. That's pretty much the best you can do in this case. You can prove you can't really simplify or speed this up. If you allow concurrent writes, so again, this letter is the important part, you can do the matching part in constant time. This is not obvious for the duels, but it can be done. And we've shown that the last step can be done in constant time. That's the parallel AND. But it turns out the pre-processing, finding the witnesses, cannot be done in constant time. You still need this log m curious time for computing the witnesses, and you can't really improve upon this. But that's more, I mean, that's for your curiosity, say. As you've noticed, I haven't really told you anything about the details of these methods, so that's just more of an outlook. Okay. What you should keep is all the things about the embarrassingly parallel tricks. You can often get a work inefficient but parallelly fast algorithm by just doing all the tasks in parallel in a simple way. And then you can often get the work down by using blocks and using an efficient sequential algorithm inside the blocks. But to get beyond that, you often need problem-specific insight. But that said, for many practical applications, it might be good enough to do a combination of blocking of the right size and some reasonable sequential algorithm inside the blocks. That brings me to the end of Unit 5, and pretty much the end of parallel processing for now.